I'd rather just get rocking and rolling, but if you have something you want to say, you can.
Okay, Adam. Adam has 15 years experience as a technician and trainer in the automotive industry. He is an ASC certified master automotive technician. Adam has been involved in racing and owned his own training company in Seattle, in the Seattle area. His dynamic teaching style is contagious, ensuring a positive learning experience for CTI customers and all. Adam has been with CTI since 2000 and teaches in California, Oregon, and Washington. And we just want to thank you for being here today. Thank you.
Hey, well, thanks for having me. And I guess without further ado, I'm gonna go ahead and take this over if you wouldn't mind, and get going. So as we kick this off, let's just make sure. I'm gonna ask you guys if you can see my screen, okay? Because I am not running a confidence monitor today. So I don't know.
See it.
You can see it. So it's welcome to our marriage screen. Perfect. All right. Well, then I'd like to get started. Look, you guys read the introduction to this class on the marriage of scan tool data and raw scope data. And look, there is really no way that 1 hour will give justice to a topic like this. I mean, gosh, any one of even just the pictures on the screen right here, any one of those would take an incredible amount of teaching time. But I'd like to start off, first of all, with the program that we have. And for those of you who are not aware of our program, the CTI online program that we have, if you could go to our website at ctionline.com, if you come over to the training tab and you click on virtual classroom, you can get a link to our
analyzing scan tool data to figure out what's.
Yeah, we have a little bit of feedback right there. I can't really see who's talking. Great, if you could take a look at that.
This one.
Okay. All right. So at any rate, guys, if you could go to ctionline.com, this is our website, click on the training tab, go down to virtual classroom, and you can get a link to the different classes we have. And guys, these classes run on East Coast and West Coast time. And of course, across the nation, there's a lot of options for you there. But I like to say that our program is a great mixture of not just lecture, but we also have live demonstrations. And I'm hoping in this hour that I have here, I can kind of present that to you. So before I get going too far into this topic, I have heard, I think, just about every excuse out there. When I built this slide, I did not. Honestly, I really didn't mean for it to be this rude. But then once I reread it, I'm like, you know what? It might be rude, but it's actually the truth. Look, I hear this. I don't have time, and the scan tool's the fastest. It's accurate enough. Or I don't have the right equipment. I can't read the waveforms. Guys, there's absolutely no excuse for this. And I am going to make one comment. I highlighted it in red. Right here, I said, look, every one of the tests that you're going to see in this program, including many more, could be individually done in time frames of 5 to 10 minutes, only if you practice regularly. And, you know, when it comes to automotive repair and diagnostics and the game we all play, you have got to practice regularly, and some of the best practice you can get is on known good cars. Dang it. If you take the stuff that I talk about today and you go, hey, I'm going to wait until a broken car comes in, and a month down the road, a car comes in, and you go, man, Adam was talking about that. We can now try this. You're going to look at your equipment like a goat looking at a watch and not even understand what the difference between good and bad is. So think about this as we go through this. Now, I got to admit, down here, I said, well, in-cylinder compression transducer testing, okay. That is an access permitting type of thing.
Technical deal at Washington, not paying bills always.
That is a time and access permitting style thing. It might take a little bit more. But if you really think about this, how much time and money do we commonly waste due to inefficient diagnostic procedures and equipment? So I'm going to start right off, rather rude, but I'm going to do it again. I'm going to say, you know what? All scan tools are liars until you prove they're telling the truth. And I'm going to follow this up with a case study here. And the first thing I'm going to bring up is some basic scan tool data. Look, all of us as technicians have used scan tools over the years. And there's no doubt that most of us realize that the information and processing time and speed from the vehicle's computer to our scan tools, our graphing capabilities, all these have gained tremendous advantages over the years. And you might even look at it and say, Adam, I can take my scan tool, I can graph the data, and it looks like a lab scope waveform. I get good graph data. Of course, that depends on the scan tool being used. There are limitations on some are better than others. But the reality of where I'm headed with this is I truly believe that a scan tool is one piece of equipment, your lab scope is another piece of equipment, and unless you combine the two, you are not getting the full picture. As I stated here, look, comparing a scan tool to lab scope is like comparing apples and oranges. Look, the scan tool gives you, as you're very well aware, processed data. It is the interpreted value from a raw piece of data that the dude in the dash has taken, assumes is real, and then processes it, sends it to your scan tool, or what I call the dude's interpretation and calculations of what happens on the car. The first thing you need to do, and you'll see this time and time again in this small presentation, is if you're looking at data on your scan tool that you're questioning for its accuracy, you have to go in and make sure that the raw data agrees with what the scan tool is presenting to you. And until you prove that your data that you see on your scan tool is true and correct, it can be extremely misleading in diagnostics, as you will see perfectly in this case study. Now, look, I'll go ahead and apologize for the quality of the picture I put on your screen, because frankly, this was just a car I diagnosed. I didn't plan on turning it into a case study, but it backs this up perfectly. We're looking at a 2001 Audi A6. This is a 2.8 liter V6, naturally aspirated, all-wheel drive automatic car. The small story behind it is that this vehicle broke a timing belt and bent some valves. Those of you with some knowledge of this platform realize they run 5 valves per cylinder, and it's a lot of damage when that happens. At that point, the shop owner decided to buy the vehicle from the customer because he was going to buy it, fix it, and then sell it to probably make a profit or whatever it be. But he bought the vehicle. But his thoughts, and I agree with him, he's a great friend of mine. He goes, well, Adam, I'm going to buy this Audi. It's beautiful. It's all-wheel drive. I'm going to get a used engine and a used transmission, and I'm going to install it in this. But before I install this engine, and here's one of the keys to this, before I install the engine, I'm going to put a fresh timing belt on it. I'm going to put water pump on it, and I'm going to go through and seal up all the common oil leaks that these vehicles had, fix the tensioners, on and on and on. So he's trying to do the most complete job he can to this used engine, plop the trans in it, put it all together, and boom, be on the road. But if you look at this, here's where the problem started. Once the vehicle was completed, I get the telephone call and he goes, Adam, this thing has low power, and it's low power. And I said, okay. And I'm trying to give him some ideas on which direction to go on this. And he goes, well, Adam, there's 4 fault codes that pop up in this. And if you look at these codes on the screen, and I'm using the VCDS, the VAGCOM, as some as you referred to it in the past, but the 4 codes, the first one I noticed that gets my attention is on the top. And it says that the pressure sensor for the brake booster has a short to plus intermittent, or basically I interpret that code as this vehicle probably has low vacuum. That's what I pick out of it immediately. And then to follow it up, he's got camshaft position sensor issues on both cam sensors that are stating they have what they consider to be an implausible signal intermittently. And then the last one, the main engine speed sensor, also no signal intermittent. So I have 3 codes coming out of this that state, I hate my cam and crank synchronization, waveform, something. I hate my cam and crank sensor. Fine. But we also have what I consider to be low vacuum. Now, at this point, and I think most of you listening, the response, at least mine, was, gee, guys, when you put the timing belt on this motor, did you use the tooling required to do that? Did you have the crank lock? Did you have the balance bar? Did you use the tools to set the cam timing up properly? And that's exactly when you get the answer that's relatively common. No, I marked the old belt and we put it on like the old one. Hey, think about that. Out of an engine you got out of the wrecking yard, you're going to trust marking the old belt and putting a new one on. I'm not laughing at him. I'm just saying, guys, use the tools. Come borrow mine. At any rate, they pull it back apart, they double check their cam timing, and the cam timing, according to the proper tooling, was actually perfect. So it was at this point I'm trying to describe other testing techniques we can do to figure out this car. And he basically gives up. He goes, no, Adam, I'm just going to send the car up to you. You look at it. When I got the car delivered to the shop, I didn't truly understand what he meant by low power. When I say low power, I swear to you guys, if I pulled this up against a speed bump, it didn't have enough power to pull itself over. As a matter of fact, to throw just another little curveball in this, that first code that says I have pressure sensor issues for my brake booster, and I said I might take that as low vacuum, this engine produced 4 inches of intake manifold vacuum. Now, I'm a C-level guy, and I'm here to tell you 4 inches of idling vacuum is absolutely not acceptable. Massive lack of power. But here's where the thought process comes in. So if you think about what I just told you, having an engine that produces very low engine vacuum and consequently very low power, there should be some thoughts that come to your mind immediately. And in the interest of the cramped time that we have here, I bet most of you would say, Adam, maybe we have a mechanical problem. We could have restricted exhaust. We have cam timing issues. We could have actually a grundle of mechanical issues that cause low vacuum. We could also have, if this vehicle were equipped with it, EGR valves that were stuck open or of the sorts. The one thing, though, that I run into the field that a lot of guys miss when we talk about an engine producing low vacuum, aside from mechanical issues that are relatively obvious, is ignition timing. So I'm looking at some scan tool data I pulled off this car that says, Adam, my ignition timing angle is 6.8 degrees before top dead center. By the way, you'll also notice an extremely low idle value right there. But here's the thing. I absolutely guarantee you that the ignition timing is either 6.8 degrees before top dead center or it's not. And this is where I'm trying to get at the point of marrying the scan tool data to the oscilloscope waveforms and understand that I may be looking at lying data. So as I look at this number and I said, man, this is either telling me the truth or it's lying, I need to have a way to prove what the answer is. Is it true or is it not? But when's the last time you tried to take a timing light to a 2001 Audi A6 and check the ignition timing? And you guys know that's freaking ridiculous because you're not going to have timing marks. You would have to go in, build your own marks and take time. And I know some of you listening, because I recognize a lot of the names out there, are going, Adam, that ain't the way we do it. We're going to take a waveform. Well, fine. Let's take a look at one of our options of marrying our lab scope to our scan tool data. Yes, I realize this is a Mercedes. Heck, it's a V12 at that point. It doesn't matter. What I'm pushing towards here is the idea of, instead of using conventional mechanical gauge testing to check compression, if we were to use an in-cylinder pressure transducer to read the signature or pressure changes of that cylinder, we can extract far more data from that car than a standard compression gauge. But one of the things that I notice out in the field is some technicians look at in-cylinder waveform testing as a way to verify mechanical integrity of the engine. What I'm trying to show you here is, there's far more to this than just looking at how do my intake valves seal? How are my exhaust valves? How's my piston? How's my cam timing? Oh, sure, that's all included in the picture, up to and including the possibility of restricted exhaust, but there's more. The problem comes in here. All right. The problem that comes in here is that it's really easy to overcomplicate things as we go along. I look at this picture, for example, and you guys should see a known good in-cylinder compression waveform of a four-cycle engine at idle. That's what you're looking at on the screen. I remember when I first learned how to do this testing, and I was overwhelmed. That would have been in the early 2000s. I was at a conference back east, and Bernie Thompson, incredible instructor, incredible knowledge base, introduced myself and a group of other instructors to this style of testing. I will never forget sitting in that room, watching him present as he's talking about the pressure changes as they go up and they come down and they go across. And he's throwing out these measuring points and everything. And I was totally lost. I was so confused. I'm looking at it going, what is all this? What does it mean? And myself, like many other technicians, got a little bit, I don't want to say we backed away from it, but it was just too complicating. Look, there is no question that every one of these measuring points that you see, A through M, there is no question that those are all extremely valuable measuring points. But there's also a point where we as technicians need to get started using the equipment, get started looking at the waveforms, and just take the basics off the top, all right? Here's what I've done to help you guys if you're interested. And most of my students all over the West Coast have already got this information from me. But I produced a cheat chart, and I'll grab one here. I certainly don't know how well you'll see this here, and I don't expect you to be able to see this clearly. But here's what I did. I took and built what I would call known good compression waveform cheat chart. And when I built this chart, what I tried to do was to put some extra value into it to try to give you an idea of when you took that compression gauge out of the picture and you put the pressure transducer in the cylinder instead, and you saw the squiggly line go across the screen, what does it mean? To help you out, what I did is I marked the actual compression waveform. I broke it down into 30-degree increments. I took every one of the measuring letters you see on here, up to and including the piston's true direction in each one of the quadrants, and I wrote a story about it. I wrote a story, like you see on the screen right here, of what every one of those measuring points is and should be, highlighted in this. On the second side, I zoomed in on the bottom to give you a little more detail. So in one page, a front and a back that can simply be printed and laminated, I have a literal cheat chart in my hand that can live in the shop next to my lab scope. So when I take the squiggly lines, when I see this come off the vehicle, I can say, dang it, man, what is E supposed to be? What is F? What is H? What is I? What are these supposed to be? And what do I expect as good and not? If you're interested in getting your hands on this, I did put my email address on the top of the screen. Guys, adamtheautoguy@gmail.com. Email me and we'll talk about how you get your hands on one of these. But from this point forward, I just want to make this far simpler for us, far simpler. When you are beginning to take waveforms, like in this case, your in-cylinder compression waveform, really, if all you figure out to do, and I will show you this dynamically before the end of this class, if all you learn to do is to take one cylinder from the car, overlay it over a different cylinder in the car, if this is all you learn to do, we're talking about not even truly understanding every one of these measuring points. I don't truly understand those, but dang it, I do recognize something. I realize that from one cylinder in the car to another cylinder in the car, or one bank to the other bank, if I found a way to take that in-cylinder compression waveform, yeah, there's some rules to it. I printed them in my document, but if I could overlay those, I know that one cylinder should look identical to the other cylinder. And like the picture I put on the screen as my example here, you should say, but Adam, if this is one cylinder overlaid on another cylinder on, as you can see at the top, this 5.7 Hemi Charger, you can say, but Adam, this doesn't look the same. This point G certainly doesn't look the same, but I see some continuity across here on the intake. Now, not going too far outside of my little box today, I will tell you, you're looking at an absolutely picture perfect flat exhaust camshaft lobe. And of course, we know the 5.7 Hemi is good for that. And heck, if you need a picture to go with it, there's a flat lobe. My point behind this was, if you take nothing else out of this class today, nothing else, Understand that at least one cylinder should look like another cylinder. Now, that's from a mechanical standpoint. With that being said, I want to go back to our Volkswagen. See, here's the problem I had with the Volkswagen in the beginning. I had ultra low vacuum. I had massive lack of power. I had a computer. I had a dude in the dash that said, I hate my crankshaft sensor. I hate my cam sensors, and I needed direction. But the whole reason I went this direction with you guys is to prove that all scan tools are liars until you prove they're telling the truth. And remember that my live data, the data I took off this Volkswagen, said the ignition timing was 6.8 degrees before top dead center. Now, not understanding anything else about an in-cylinder compression waveform, this point right here, what most of us refer to as point A, is the highest peak pressure found in that cylinder. I know I'm going to set some of your guys' hair on fire, but I'm going to tell you, point A right here represents top dead center of the compression stroke. I know there are variables. We're not getting into that today. But if this is top dead center of the compression stroke, and then it does it again, we could say this was top dead center of the compression stroke. It went down and up to its next top dead center of the compression stroke. But I have added one extra channel of my lab scope here. I added in red the actual ignition timing, or the true ignition strike delivered to that cylinder. It doesn't matter what cylinder it was. Heck, maybe it was cylinder number 2, or nope, I wrote it on the top. It was number 4. It doesn't matter. But when I take an in-cylinder compression waveform, like you see here, I like to add things like the ignition for that hole. I add the injector for that hole, as maybe you'll see later if we have the time. But this dictates an absolute lie from my scan tool data as I see with the raw data on my scope. My dude in the dash said, Adam, we believe we're 7 degrees before top dead center. That would have put that strike over here before the top dead center marker. But contrary, this is, gosh, guys, I don't know if you can read these numbers, but I'll tell you, this large mark right here is 30 degrees after top dead center, and it went another 10 after that. This timing is actually 40 degrees after top dead center. Now, I don't know how many of you guys have driven a car with the ignition timing 40 degrees after top dead center, but I can tell you they don't run good. Actually, they're very poorly. But now there's something to think about here. See, this ignition timing, it isn't off by 40 degrees because the dude in the dash, according to the scan tool data, thought it was happening about 7 degrees before. It's actually happening about 40 degrees after. This is what I consider to be a creepy number. When you deal with circles, there are creepy numbers. There are things like 0 degrees, 45 degrees, 90 degrees, 360 degrees, 720 degrees. There are some basic numbers that have a creepy factor to them. If I took the few degrees before top dead center and added it to the actual strike, I would realize that this ignition timing is 45 degrees after the true delivery, 45 degrees after that piston hit top dead center. But the dude in the dash thought it was over here. That's got to lead you, guys, that's got to lead you to only one sensor on the car. What one sensor on the car could be misconstrued and tell the dude in the dash, or make him think the piston is in one position when it's off by a creepy factor of like 45 degrees. And the answer in this case was that the reluctor ring had been installed improperly on the back of the crankshaft. And yes, this crankshaft reluctor ring, guys, is the flex plate. So engine and trans must be split. But before you say it, because I know you're thinking it, you're going to say, oh, no, Adam, I worked on a lot of these cars. This flex plate only fits one direction because it has offset holes. Well, let me let you in on something. It'll fit more than one way if you try hard enough. We've seen this stuff. But, you know, the reason this flex plate got put on incorrectly is the bolts are gigantically long. They're huge bolts that go to this, long bolts. So when the technician was holding the flex plate up, he was able to literally start all the bolts. And when he ground that down, it just spun it one hole off, equaling the misunderstanding. So, okay, I just showed you something on a Volkswagen. Why don't we take this same basic concept to another car? We're now looking at a 2010 Dodge Charger scan tool data with a 5.7. Once again, same complaint. Very low power. A little bit of story to this car. This vehicle actually flattened a camshaft and was sent to the dealer to have the camshaft replaced. They put a camshaft and lifters in it, and it had low power ever since. They did an incredible amount of diagnostics, include replacing the injectors and the ignition systems, and even replacing the ECU. At this point, the fleet, it was an Oregon State Patrol car, not that it matters, but at this point, the vehicle wound up at one of my shops, and they called me on this, and they said, Adam, this thing's got horrible power, incredibly low power, but it's had all this work done to it. Where do we go? I said, well, let's take a look at some data. Granted, I have compressed down my approach, but I would like to draw your attention to this portion of the screen right here. I have a knock sensor at idle on this 5.7 Charger. I have a knock sensor producing about 0.5 volt. I have my other knock sensor. Now, if you're not familiar with these cars, the knock sensors are under the exhaust manifolds, one bolted to each side of the block. I have one producing 0.4 volts. I have one producing 1.5 volts. I have a knock retard of 0 degrees. I have a base spark calculation of -41 and a spark advance of 10.5. Here's the problem I run into, and every technician out there runs into the same thing. Are those numbers acceptable or not? Are those acceptable numbers? Yes or no? Well, I will thank myself for this, but they had another vehicle I could compare to right next to it. Looking at a known good version of the same car at idle, we have about 1/4 volt on each knock sensor. We have 0 degrees of knock retard. We had a base timing of basically -40 and a spark advance of 10 degrees. Known good car, perfect car. My car has basically the same spark, base spark, the same spark advance, no retard activity, but very odd knock sensor result voltages. So I ask myself again, when we're marrying scan tool data to LabScope, I ask myself, Adam, are these numbers telling the truth? Maybe the easiest one to see is my timing truly 10 degrees? Because these numbers and these numbers look the same. So let's take a look at a known good car. Utilizing the same concept we used of looking at in-cylinder pressure waveform, I have added my spark event for the cylinder, and now you guys get to see something extra as some of my favorite captures go with in-cylinder waveforms. I like to add the injector pulse. And the injector pulse, by the way, is in perfect timing in this engine, happening during the exhaust plateau beyond the scope of this class. Where I was headed was, where is your spark truly being delivered? Because on your known good car, he said 10 degrees, 9.5 degrees is where he thinks the spark is. By mechanically looking at it and taking the measurement, it is happening before top dead center at a factor of about 11 degrees, which tells me my known good car is not lying. I verified these numbers look great. Yet, on my bad car, we saw the same, almost exactly the same, massive retarded ignition timing. But what's frustrating about this one, what's frustrating about this, look, I quickly can tell you, hey, that scan tool's lying, because back here, he said it's supposed to be 10 degrees before. It's not. It's 30 or 40-ish after. He's completely wrong. Could he be wrong because he has inaccurate knock sensor data? And of course, my thoughts are simply that. I'm like, look, maybe you do have bad knock sensor data. After all, we shouldn't be seeing hardly anything. So what do? I go unplug the knock sensors. The kicker about this car is by unplugging the knock sensors, my voltages stayed the same at the PCM. Now I want you to chew on this thought. I know I'm condensing this and I'm going quickly through it. Here's what I want you to think about. A good car produces a 1/4 volt on each knock sensor at idle. My car had 1.5 on one knock sensor and 1/2 a volt on the other knock sensor. When I unplugged the knock sensors, those voltages were still there and very similar to what you see on the screen. Would it make sense to you guys? And it did to me at the time, and it still does now. Would it make sense to you to look at that and go, woo, I might have an ECU issue. I might have a a ground issue. Heck, I might have a wiring harness issue. And then some of you may remember, well, Adam, they already put a new ECU in it. I understand, but that's hearsay to me. Here's the thing. I thought that the best next approach would be to unplug the knock sensors from the computer and see if my numbers stabilized. Well, fortunately, I'd rather be lucky than good. When I unplugged the connector, coolant splashed on me, all right? Not only coolant splash out when I unplugged it, I did go out and find that the coolant sensor had internally ruptured and had filled the wiring harness with coolant. There was no problem with the ECU. There's no problems with the knock sensors. And the data that's lying from the computer was because it had coolant in the wiring harness. I would have never, I could have been lucky and found that, but I would have never gone that direction without that approach. So we've got about a half an hour left. Let's look at another marriage of scan tool data and lab scopes. What I'd like to do now is utilize lab scope data to decipher fuel trim errors, but I'm also going to include what I call live software demonstrations. Now, I said that in our CTI virtual classroom presentations that I like to do some presentation, lecture style, like I just gave you, 30 minutes of freaking lecture, but I also like to try to add in some live demonstrations. And here's where I'm going to show you an example of that. I'm going to start with some graph scan tool data. Guys, this is taken with the Snap-on scan tool. Doesn't matter to me what brand it is. And in the interest of time, I'm not going to have you searching all over. I'm going to draw your attention. I'm going to draw your attention to these two graphed data PIDs right here. Now, guys, I have not been paying attention to the chat room. I don't know if that anything's gone through yet or not. If you guys have a question personally, I have no problem with you unmuting your mic and just interrupting me because I will haul until that happens. So if you have a question, spit it out. I'm not ignoring you. I just get in a kind of that zone. All right. At any rate, here's what we're looking at. I am looking at long-term fuel trim on bank 1. I'm looking at long-term fuel trim on bank 2. This is a 2003 Ford F-150, all right? Now, as I look at this value here, the first thing I want you to notice is that if you just look at the current value, it's the simplest way to break through all this data. I am adding 22% long-term fuel trim on bank 1. I am taking away 23% long-term fuel trim on bank 2. I have what I refer to as opposite fuel trends, bank versus bank. So here's what we start to think, or at least I start to think. I look at it and say, why on a mass airflow controlled vehicle, how could I have a supremely positive on one bank, negative on the other? How could my fuel trims be opposite? Well, there are some basic things that come to mind, guys. Maybe the oxygen sensor connectors have been swapped. Lord knows we've seen that out there. Maybe they're swapped. Maybe this breathes differently, one bank versus the other bank. And when I say one bank breathes differently than the other bank, maybe I'm saying one bank has a restricted catalyst and the other doesn't. Or maybe one bank has different cam timing than the other. So I'm still looking for the most efficient way, at least in my mind, to determine where to go. My data tells me, my scan tool data says, I think there's a breathing issue bank to bank. Then wouldn't it be smart, guys? Wouldn't it be smart to do a test with our lab scope that would give us as much information as possible. For example, this is the in-cylinder breathing. Yes, it dictates things like cam timings, and I already told you in this class, I'm not getting into all these measurements. But the other thing that this test has the ability to dictate to you is the exhaust pressure. I could use one test to be able to look at cam timing and exhaust pressure and quite a few other things, by the way, instead of doing multiple tests. So by doing this test, I get to look for that possible plugged exhaust. But here's where I wanted to keep this so simple for you. If you guys have been sitting back, you really want to pay attention to this part right here. What we did on this, we chose one cylinder, okay, bank 1, and another cylinder on bank 2. They happen to be cylinder 1 and cylinder 5. But here's the key. I take my in-cylinder pressure waveform. Now, I've taken a snapshot of this in the interest of time. But what did I try to tell you earlier? I said, if you come away from this class with nothing other than learning how to superimpose one waveform over another, you won the game. Let me show you how we do that. We'll do that one actually live. So here's what I've done. I found a program, and I'm going to open this program up for you, and you guys probably want to write this down if you're not already familiar with it. Over the years, there have been several programs released, ETOs, TDCs, compression waveform viewer, there's a few of them out there, that have allowed us to do some manipulations of intake waveforms, exhaust waveforms, fuel waveforms, in-cylinder compression waveforms, and throughout the years, some have fallen away and some have come back. There is still available a free program called Pressure Waveform Overlays. This is what you might want to write down. Pressure Waveform Overlays can be found in the Microsoft App Store and will be only usable, at least from what I've seen, on Windows 10. But you could go right now to the Windows App Store and download Pressure Waveform Overlays. When you download that, you will get an icon that looks like the one I'm pointing on the bottom of the screen here. That is my Pressure Waveform Overlays. The trick is, how do I use it? Watch this. I'm going to go ahead and take one of my waveforms. So think about this. Some of you recognize this waveform as taken off the Automotive Test Solutions scope series. Some of you have maybe something as simple as a single channel U scope from AES Wave. Maybe you've got several Pico scopes. Maybe you've got a snap-on scope. I don't care what you use, the Autel Maxi scope. This will work with any scope, and that's what makes this so cool. What you do after you analyze your waveform and you pick out a pair of events, like I picked out on this screen, what you do, at least what I do, is I will simply take a snipping tool and I will take this snip of an event. So there is an event right there. Now understand something, guys. Even if I've got a lab scope that I can't transfer to a PC, I can take my cell phone and snap a picture and throw it in here and do this. So I'm going to call this snip, I'm going to save it, and I'm going to call it cylinder 1. So we'll just call this 1. All right. So I just saved that one. The next thing I'm going to do, and you know I'm headed here, is I'm going to go to my cylinder 5, and I'm going to do the same thing. I'm going to snip that. So here we'll go to snipping tool, and I'm going to snip my cylinder 5, just like that. Bang. I'm going to save that. And I save all my stuff to the desktop, by the way, but I'm just going to call that 5, enter. Here's where the magic comes in. Magic comes in when I open up my pressure waveform overlays. I minimize it a little bit right here. And I take one of my snips. I right click on it. I copy it. I right click. I paste it into this program. Now, here I have inserted a fully adjustable compression waveform onto the plate of this. I can stretch it wide, short, whatever I want to do, but I can also do some magic. I can come down here. I can put a cursor at my top dead center. I can put another cursor at top dead center. Once I do that, I can hit this button at the upper left and lay in. a set of pre-arranged markers. Guys, you can do this with anything you can take a picture of. Cam sensors, crank sensors, intake waveforms, exhaust waveforms, man. Your imagination is the only thing holding you back. But here's where it gets even better. See, I have marked this waveform where if I had the knowledge, or if you had a chart or something, but if you knew what A was supposed to be, what D was supposed to be, I now have the markers I need to analyze this waveform. But where I'm headed is a little bit different, because I'm going to go ahead and minimize this again. And now I'm going to take cylinder 5. So let's take cylinder 5. I'm going to copy it, and I'm going to paste it. Now I have 2 waveforms on my palette. Now I'm going to take this, and I'm going to put it over the top of this one. Now I have a little opacity meter. I can dim it down. I can bring it back. I'm going to dim it about half. And now I'm going to take this. I'm going to start doing the stretch. I'm going to stretch this waveform to where my towers line up. So let's stretch this around here, and we will get this to where it lines up. I'm going to grab this on the bottom, move that up. As I stretch around, and as I move this and get everything lined up, I hope you guys can see what I've done. And I tried to explain to you, if the only thing that you take out of this class is how to do what I've just done, I don't really care about all those measurements. What you should very easily be able to discern is that my exhaust valve opening is happening differently on one bank. I've got one exhaust happening significantly before the other side. I've got an intake that happens differently. There is no question in my mind that one camshaft in this engine is operating at a different piston position than the other side. And guys, I don't even have to be a genius at this. I don't have to say, well, Adam, it's advanced by 30 degrees. I don't have to even get that carried away. Oh, I certainly would, but you don't have to. All I have to do is look at this and say, hey, boss, there ain't no spark plugs, injectors, throttle body computer in the world that's going to fix that fuel trim error, because mechanically one bank breathes differently than the other. You're done. That's it. It's out of mechanical time. By the way, not to get too carried away on this live demonstration, but it also does give you the ability to put this on here. I thought this is kind of neat. I can actually take this and move this to the exhaust valve opening and the closing. And so I can actually add some colors to this, print this out, and look really smart to my customer if I want to. It allows me to do annotations. It allows me to change colors. It allows me to also use this feature. Let's see, number of cylinders. Let's pick a 4-cylinder, a sync of 1, and let's do a 1, 1, 3, 4, 2. All right, go. You also have, as many of you have used in the past, an overlay to where you can look at intake, compression, expansion, exhaust. So you can overlay this right here over intake waveforms, exhaust waveforms. So when you're doing intake manifold waveforms, exhaust pressure pulses, that is also included in this software. And like I said, for free, you really can't beat the price. But what's cool about it is the adjustability, the flexibility to use any lab scope in the world. Heck, you should see me sitting here in my little studio here. And I find it funny. Brandon looks at it and says, it looks like his sock drawer. I've got equipment laying all over right here, but constantly during the days, I get waveforms sent to me. And you know what? A lot of times the guys will just text me a compression waveform. Hey, Adam, what do you think of this? This gives me the way to take even a picture off my phone and analyze it without having the raw waveforms. At any rate, guys, there's a live demonstration of that. And now I want to go back and talk a little bit more about this car. What I just proved to you on this 2003 Ford V8, 4.6, whatever, it's an F-150, it doesn't matter, is that the cam timing from one bank is mechanically different than the breathing from the other bank. By the way, looking closer, you'll realize the exhaust plateaus were similar. It was literally a cam timing issue. So we ended up with something like this, right? Well, Adam, what should it have looked like? That. Look, when I say that we should be able to overlay one cylinder over another cylinder and that they should be close, guys, look at this. This particular overlay is one bank versus the other bank. There was a small difference in peak compression of 5 pounds, but I had a little bit of an RPM difference. Those rules are for another class. There's quite a few rules to doing this. But what I wanted to get across to you is you'll notice as I decompress and I come to the point of the exhaust valve opening and it ramps up, and my exhaust plateau and the drop into my intake event and the depth of my intake plateau and the closing of my intake valve, my one bank looks identical to the other bank, indicating at least the two banks breathe the same. So when I say they need to be close, I'm telling you, they need to be that kind of close, not this kind of close. So let's try another topic. And I've got just enough time to squeeze maybe this and another one in, so here we go. I have a 7.3 power stroke. Okay, it's a diesel. When I got called to go look at this vehicle, when I got called to look at it, their problem was that it had a P0470 code in the scan tool data. Also utilizing the scan tool to run the key on engine running test. So we're using the scan tool. We're running the test. It constantly resets this P0470 code. So the scan tool and the dude in the dash is saying, Adam, I've got a problem with my back pressure sensor. Come on, guys. I know you guys are professionals out there, and I bet you're going, Adam, man, it's a 7.3 power stroke. It either has a plugged tube or a bad back pressure sensor. Guys, come on. It's a Ford power stroke. If you look at the 7.3 power stroke, the 6 liter, the 6.4, the 6.7, they all ran back pressure sensors, and they were problematic on all of them. And this one was no different. Heck, the shop looked at this and said, he hates the back pressure during our key on engine running test. Let's put a sensor in it. Let's put a sensor and let's put a tube in. Well, that didn't fix it. Then their next step is, well, how do we create back pressure? Well, beyond the turbo, there's a blade on this one that they close to produce back pressure. Guys, that blade was gone. There is no blade in there. So they sell a turbo. They put the turbo on and the turbo pedestal to handle the oil controls. It still doesn't pass the back pressure test. Now you got to understand, in the state that this was done, it was Fresno, California, if you care, but they have to clear this or it's not going to pass emissions. This has to be fixed. The turbo and the pedestal didn't do it. Well, then they realized it's got cracked exhaust manifolds. I mean, this is the typical rabbit hole we find ourselves shooting down. Well, if it's got cracked exhaust manifolds, it can't build enough back pressure. Let's fix that. Okay, so we've got manifolds, we got a turbo, we got a pedestal, we have back pressure sensor and tube. It's still set in this code. Guys, when I went to look at this car, this was my absolute first approach. Once again, I apologize for the quality of the picture. I'm just trying to diagnose and fix a car, man. But this turned out to be a great picture because it now gives me the ability to add my lab scope to my scan tool controls and look at what's going on under the hood. But I got to tell you guys something. I got to tell you, one of my favorite first tests on a lot of different applications is what you see right here, wrapped around the battery cable. Most of you would recognize this as a high amp current probe. Yes, it's on the positive cable that heads down to the starter. Heck, if you're familiar with the 7.3 power stroke, you might even recognize these little wires right here, because this is my remote starter button switch going to the starter solenoid on the side so I can crank it over. And if you said, Adam, you're going to do a cranking relative compression test, you'd be obviously right. I'm going to start with a cranking relative compression test. After all, you cannot expect an engine that has back pressure controls in the exhaust to be able to produce enough back pressure if it has cylinder issues. It only makes sense to me. But the real key to this picture was the other tool I added to it simultaneously. And I got to admit to you, over the years, this has become, I don't want to say habit, but I do this a lot more than I did years ago. because you'll notice that I have a pressure transducer also hooked to my lab scope. But my pressure transducer, if you follow the hose, goes to the oil dipstick tube.
Okay, I thought you were on a glow plug.
No. Thanks for bringing that out. That goes to the oil dipstick tube. Now I want you to chew on something. If you are already going to go through the hassle and all the time involved with doing a cranking relative compression test, why not gather a little bit more data? And some of you are sitting there going, well, dang, Adam, I'd like to add an intake manifold waveform and an exhaust pulse waveform. And of course, I'm that geeky dude sitting on the other side of this camera saying, oh yeah, the more channels, the better. I mean, geez, guys, I've got three different Pico boxes. I've got a 4-channel 3000 scope, a 4-channel 4000 scope, an 8-channel 4000 series. But if I open a Pico 6 beta, a Pico 6, and Pico 7, I can have 16 channels on my screen at once. And that is some whacked out, geeky stuff. Okay. But the point I'm getting at here is the more data, the better. But in this case, I can at least get to look at pulses in the crankcase during the cranking relative compression test. And when I did the test, here were the results. Now, guys, look at this. It's game over. Stick a fork in it. And I'm looking at this, and you know, as I'm talking to the technician, he's going, Adam, why are you starting with this test? Because I'm lazy, man. I am a lazy technician. If I can find a faster, easier, more efficient way to do something, I'm going to do it. But this, thankfully, in this case, gave me detail. Because for those of you familiar with a cranking relative compression test, once again, it's a little bit out of the scope of this class, but you guys are professionals. I'm sure you guys are performing something along these ideas anyway. If you look at the overall current, I averaged my peak currents to right around about 460 amps. The problem should be very, very obvious to you that as I go up on the compression stroke and the current increases to the starter and then drops and current increases, I have 2 cylinders in a row that are producing 50 less amps of current when going up on the compression stroke. And you're saying, Adam, you've got 2 cylinders that, at least from a relative standpoint, don't have as much compression as everybody else. That's right. But adding the dynamics of my crankcase pressure, which you see in red, or this channel B, you will notice that at the same point in time, and this is why these 2 tests go so good together, you notice at this point in time, at the same point I have low compression, I have bursts of pressure in the crankcase. Guys, once again, man, it's game over. Ain't no cylinder heads in the world gonna fix this, man. This thing has problems with blow by from the pistons. Now, whether you're dealing with rings, whatever, I'm not going to get into that part of it, but I would never be able to expect the scan tool to be able to run and complete the back pressure test if I have 2 cylinders that may not even be contributing. And I know the argument, I've been doing this a long time. Well, Adam, was it running rough? Yeah, it ran horrible when I got there. I just need a starting point, and that was a dang good one. All right. Now, I've got just a few minutes left, so I'm going to try to jam one more live demonstration in for you right here. You Pico users will probably appreciate this if you weren't already aware how this works. I have a 2009 Dodge Charger with now the 2.7. Sorry, I don't want to hurt anyone's feelings, but questionable. At any rate, the Charger 2.7 V6 came into the shop with fuel trim errors once again. I have, and once again, sorry about the picture. I'm just doing my job. I have a long term of -16 on one bank and a long term on the other bank of a +5. Not near, guys, not near the deviation we saw on the Ford truck. You got to understand something. This is not a mass airflow controlled car either. This is a speed density controlled car. So the way that base fuel structure is created is a little bit different. But I still approach this the same way. I see I have a difference in fuel trim in opposite directions on each bank. So here's what we're going to do. I'm going to go ahead and drop into this, and let's take a look at the raw data that I pulled out of this. Let's open this up. The first thing I did was this test right here. some of you may recognize this, you Pico users, as a cranking relative compression test. Even though it may seem acceptable and green to you, I see a rhythm of high, lower, high, lower, high, lower. I have already kind of got my feelers out on this. When I have alternating pressure changes, I start going, wait a second here. But I've learned something. I will do this test on the Pico platform, but I will usually, if it's questionable to me, I'll follow it up with an actual one. And so here's what I'm going to do. And maybe you guys will see this. Maybe you won't. Here is page 4 of my 6 of my cranking relative compression test. I am going to come in here and give this just a wee bit more detail. Let's bring this back up on the screen. As I gave it a little more detail, let's spread this out just a wee bit. I could even come in here and heck, let's give it a little bit of more filtering. All right. As I screw around with that, I think personally, I see a pretty darn good true deviation of better, less, better, less, better, less, better, less on this. I see it. So this leads me to think that we have a breathing issue from bank to bank on this engine. Now, unlike the last study, I'm going to approach this a little bit different. I'm going to do it with intake manifold vacuum. And I'll show you this quickly. And then I don't know how this is set up, guys. I know we're breaking the 1 o'clock or the 2 o'clock hour here. Guys,
it's okay, Adam, if you go over a little bit.
I'm going to go over just a little bit. I just want to show you guys this.
The numbers will mind.
I guess you guys can go home if you don't like it, right? That's how this works. Okay. So, but what I'm going to show you right here is I'm going to show you a little bit different approach. First of all, I'll show you the picture of it. Here's the picture of my approach. There is my scan tool. There is a wire over there. But once again, we are adding my pressure transducer. But now you see a hose wraps around. And yes, it is going to intake manifold vacuum. And so I'm going to take an intake manifold vacuum waveform, or the amount of draw that every cylinder creates. And I'm going to use the easiest sink that I had at that point. The easiest sink that I had was to get to an injector. But watch this. I have injector waveform. I don't even care what cylinder it is. It makes no difference to me. But it's got a nice firing rhythm to it. If this is one firing of the injector, we just call that 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Or I could just wing on in here and say, look, between this firing event and this firing event, I have all of them. So from here to here is one complete cycle, 2 crankshaft revolutions. Here is where a problem lies with many, many technicians. A lot of guys will try to decipher this vacuum waveform. Guys, heck, let's just zoom in on this even more. I would really like to see most technician make heads or tails of that vacuum waveform in this 720 degrees. You know what that looks like to me? It looks like a bunch of garbage. Someone would send that to me and they'd say, hey, Adam, how's this engine breathing? I don't know. Danged, man. How many suction events do you want? It looks horrible. And I got to admit, in the very beginning, now, okay, truth be told, yes, I can analyze that. Do I want to? Oh my gosh, no, I'm too lazy for that. I have a different trick. I use a method that I call super zooming and super filtering. Watch this. That looks like trash. So I'm going to come up to channel C and I'm going to super filter it. Now, by super filtering, what I'm doing is I'm telling the scope not to alter the waveform in its capture state, but I'm telling it to ignore frequencies. Watch what happens when I get down around 30 hertz or so. What do you notice here? Well, I can't see it. Now we go to super vertical zoom. Now check this out. Now, I'll be darned. I have something that's actually very legitimate to read and very legitimate for diagnostic purposes. Because what I see here, guys, I see 6 suction events. I see less vacuum, more vacuum. Less vacuum, more, less, more. 1, 2, 3, 4, 5, 6. Every alternating cylinder is producing less suction event as compared to the other bank. The timing has jumped on this car. It's got a jump timing chain. And before you say it, and this is the last comment I'll leave you with, because I could talk about this crap for hours. All right. The last thing I'll leave you with is this. Well, Adam, it's a Chrysler. If the cam and crank were out of sync, it wouldn't start. But this engine only has one cam sensor. It's only got one cam sensor on the driver's bank. Therefore, if the passenger's bank jumped, the dude in the dash is too stupid to realize it. He don't know. But that is another approach. And I know we were rushed for time on that, but gosh, guys, that's about where I'm going to stop on this. So I will, I'm going to give up control of this screen and bring you guys back. And wow, we got up to look like 48 people there. At any rate, that's all I've got for you today. But I do want to say one more thing. It's really important that you guys find a way to get this type of continuing training at your house or at your facility. And as I tried to mention in the beginning, our website is ctionline.com. We have a lot of variety of different classes. Heck, I teach an online class every Tuesday and Wednesday from 7 to 9 p.m. Pacific Coast time. Yet our other instructors are teaching Eastern time, 7 to 9 p.m., Central time. And you have a variety of classes to choose from. And in my opinion, Brenda, I'm going to say it's just foolish not to take advantage of what we have. And to take it a step further, me being a West Coast guy out here, I have a couple of my students, they actually sign up for East Coast time classes, listen to it while they're finishing up the last couple hours of work, and then they'll go on to a Pacific Coast time. So we have some people that are taking wicked advantage of the things we have. So
Thank you, Adam. Thank you, Brenda.
Thank you. And I just put the website link in chat as well. CTI Online.
Adam, we want to thank you very much for doing this for us.
yeah, well, thanks for having me. It was a lot of fun. And got to be honest with you, I'm in my studio a lot. So anything else you guys want to pull, sign me up. I'm
Oh my
in.
goodness, yes, we'll take you up on that for sure.
Yeah. Awesome.
And I want to thank everybody for being here today on our Lunch and Learn. We appreciate you, and I know that you found this very valuable information. And again, Adam, thank you very much, and everybody take care. Thank you.
Thanks.